Welcome students, my name is Raman Singh Chauhan. Today we are going to study the topic index system for crystal planes. Before going to crystal planes, let us understand crystal directions because these are related terms. So what are crystal directions? So we know any lattice vector can be written as that given by r equal to n1x plus n2y plus n3z, where n1, n2, n3 are three integers and x, y, z are different axes which we are considering for giving transformation. So we can say this R is transformation vector or lattice vector. So translational vector or lattice vector. So if we consider that if these numbers n1, n2, n3 have a common factor, in that case this factor can be removed. Suppose we are having n1, n2, n3 equal to 2, 2, 2, then we can write it as 1, 1, 1 because 2 is common in all the three, n1, n2, n3, that is all the three 2, 2, 2. Similarly, if we are having 4, 0, 0, that is n1 is equal to 4, n2 is equal to 0 and n3 is equal to 0, we can have 1, 0, 0. So in that way we can give this set of numbers, set of integers n1, n2, n3. Now what are crystal directions? So we will learn about crystal directions. That is, crystal direction means a whole set of parallel lines which are equivalent due to translational symmetry. Opposite orientation is denoted by the negative sign over a number. The equations of plane in 2D and 3D having the intercepts a, b and ABC respectively are x upon a plus y upon b is equal to 1 or x upon a plus y upon b plus z upon c is equal to 1. And crystal direction is the direction or line of axis or line from the origin and denoted as 1, 1, 1, 1, 0, 0, 0, 1, 0, etc. So what we can say, what are crystal directions? That if we are taking any crystal, suppose this is a cubic crystal, so in this crystal we can represent this crystal by three vectors a1, a2, a3. These are lattice vectors and we can represent the a1, a2, a3 as combination of x upon a plus y upon b and z upon c, or in the form that we were using r is equal to n1x plus n2y plus n3z, anything we can give the translation vector, and in that we have these axes which represent this cubic crystal. Now what are the directions? If we are taking any direction, any plane, then from this origin which we are considering, from this origin to the plane, if we are joining that line, that then that gives the crystal direction. So here we can see, and this gives the crystal direction, and for 2D and 3D we can have two different equations, x upon a plus y upon b is equal to 1 and x upon a plus y upon b plus z upon c is equal to 1. And here we can determine if these planes, how these planes are decided, that is, they give the intercept a, b and c. What they are intercepts, and those intercepts we are using, and reciprocal of those intercepts is used. If there is any intercept that is negative, then in that case we can put bar over the number. Like if 1 bar is written here, it means that intercept was -1, and for that -1 we are using 1 bar. So this is 0, 1, 1 bar plane, and in that way we can give the directions from origin to the particular plane. Now crystal planes. So what are crystal planes? Crystal planes come from the structures known as crystal lattices. These lattices are three-dimensional patterns that consist of symmetrically organized atoms intersecting three sets of parallel planes. These parallel planes are crystal planes and are used to determine the shape and structure of the unit cell and crystal lattice. So, what are crystal planes? When we are talking of crystal planes, that they are formed because of structures known as lattices, crystal lattices. And what are crystal lattices? That gives the three-dimensional pattern. And when these crystal lattices are considered, they cut the three planes. In the structure, they cut three sets of parallel planes, and those intersecting three sets of parallel planes give the crystal planes, and they are used to determine the shape and structure of the unit cell and crystal lattice. So, the planes intersect with each other and make 3D shapes that have 6 faces. So, we will understand how these planes are considered or how they make the 3D shapes and how they have 6 faces, because if we are having any cube and we are considering any plane, then that plane can be considered by taking the intercepts, and when we are taking the intercept, then we can see that this plane will be having 6 faces. That will be a 3D shape having 6 faces. These crystal planes define the crystal structure by making axis visual and are the means by which we can calculate the Miller indices. Miller indices are calculated by using the crystal planes. So, we know in the for the same thing that the orientation of a crystal plane is determined by 3 points in the plane, provided they are not collinear. That is, when we are considering a plane, then in that plane, that can be tilted, that can be straight, that can be parallel to some line, and for that, if we are considering, then that plane will be having 3 non-collinear points. That is determined by 3 non-collinear points. 3 points which are non-collinear means they are not in the same line. And if each point lay on a different crystal axis, the plane could be specified by giving the coordinates of the point in terms of the lattice constants A, B and C. So, now these 3 points, since they are non-collinear, they are on different crystal axes, then these points or the coordinates of these points are used to determine the plane, and these coordinates are called the lattice constants A, B and C. And hence, a crystal lattice may be considered as an assembly of equidistant parallel planes passing through the lattice points and are called lattice planes. So, what is a crystal lattice? That is an assembly of equidistant parallel planes which are passing through lattice points, and they are called lattice planes. So, what are Miller indices? Like we know that Miller indices are calculated for crystal planes or using crystal planes. So, what are Miller indices? So, that is a notation that is conventionally used to describe lattice points, directions and planes. They are called Miller indices. For calculation of Miller indices, we determine the intercepts of the face along the crystallographic axis in terms of unit dimensions. Here, unit cell dimensions, what that mean? That when we are determining Miller indices, we are taking the intercepts of crystallographic axis with the faces. So, in that case, when we are saying unit cell dimensions, that means it is not unit. Like if there is a crystal which is having 1 unit along x axis, 1 unit along y axis and 2 unit along z axis in that particular crystal, then the unit cell dimension which we are using, that will not be 1, but that will not be 1 1 1, but that will be 1 1 2, because we are talking of unit cell dimensions. Here the z axis was having 2 units in that crystal, so that is the unit cell dimension. It means if we are considering a unit cell of any crystal, any complex crystal or any mixed crystal, in that case we are using the unit cell dimension, and unit cell dimensions may be same in all the crystallographic axes or along all the crystallographic axes, or they may be different. So now we will talk about rules for Miller indices, like what are rules for determining Miller indices. So first one, we take the reciprocals of the unit cell dimensions or the lattice constants. Then we clear fractions if the numbers are coming 1 by 2, 2 by 3 or so, then we are clearing fractions, and then we are reducing to the lowest terms. If there is any common factor, we remove that common factor and then we reduce to the lowest terms. So that we will understand here to determine the Miller indices. For what we first do, we determine the intercepts. Like the intercepts or basis vectors are a, b, c in terms of the lattice constants a, b, c. The axes may be those of a primitive or non-primitive cell, and these intercepts may be x, y, z, and then we form the fractional triplet x upon a, y upon b and z upon c, and after that we take the reciprocal of these numbers, reduce the numbers to 3 smallest integers by multiplying the numbers with the same integral multipliers. So in that way, first what we did, we first determine the intercepts. When we determine the intercepts, like we were having basis vectors a, b and c, and for that we determine a, b, c that are lattice constants, and then we take the reciprocal of those lattice constants and then reduce to the smallest integer. So in that way we can come to form the set, and the Miller indices are the orientation of a plane or are used to determine the orientation of a plane in a lattice, and Miller indices are defined as, we find intercept of the plane with the axis along the primitive translation vectors a1 and a2 and a3. Let x is fractional multiple of a1, y is fractional multiple of a2 and z is a fractional multiple of a3. Therefore, we can measure x, y, z in units a1, a2, a3 respectively. We have then a triplet of integers x, y, z, and then we invert to 1 upon x, 1 upon y, 1 upon z, and reduce to reduce this set to a similar one having the smallest integers, that we will discuss by example. So what ultimately we are doing, we are finding the intercepts, then we are making reciprocal of it, and then we are reducing it to the smallest integers, and in this way the Miller indices of a plane are represented as HKL, that is common or that is symbol for the Miller indices. So let us consider the example. If the plane intersects x, y and z in points 1, 3 and 1, the index of this plane will be 3, 1, 3. So here we can see that there are 3 intercepts 1, 3 and 1, then index will be 3, 1, 3. Similarly, if the x y and z intercepts are 2, 1 and 3, then calculate Miller indices. So, if intercept is 2, then what we are taking? We are taking reciprocals, that is reciprocal of 2 is 1 by 2. For second 1, reciprocal of 1 is 1 by 1, and for 3 the reciprocal of 3 is 1 by 3. So, we have these reciprocals, that is and we find 1 by 2, 1 by 1 and 1 by 3. Now, what is our second step? That is clear fractions. First is take reciprocal, then clear fractions. So, for clearing fraction, what we will do? We will take the LCM, and if we are going to take the LCM of these three numbers, then we will find the LCM is 6. And so, what we will get? We will get that 2 for 1 by 2 we will have 3, for 1 by 1 we will have 6, and for 1 by 3 we will have 2. Now, what is there? Now, we need to reduce to the lowest term, that is already there. So, because we know there is nothing common in these three factors, because if we are taking 2 and 3, they are prime numbers, so they do not have anything common, and in that way we cannot find a common factor. So, this is the simplest or reduced form in the or the lowest terms. So, Miller indices are 3, 6, 2. If a plane is parallel to an axis, its intercept is at infinity and its Miller index is 0. Now, similarly, if we want to calculate for this example where points are 1, 3 and 1, so we can have reciprocals, those are 1 by 1, 1 by 3 and 1 by 1. If we take the LCM, then we know the LCM of 1 by 1, 1 by 3 and 1 by 1 will be 3. So, we will get 3, 1 and 3, and then we know that 1 and 3 both are prime. So, this will be the simplest form, and hence we will determine this plane, which we can see here by this shaded portion. This plane will be 3, 1, 3 plane, where we are having 1 unit along this, 1 along this and 3 along this, 1, 2, 3. So, this will be 3, 1, 3 crystal plane. Now, some points about Miller indices, that is a generic Miller index is denoted by HKL. Miller indices specify not just one plane but an infinite set of equivalent planes. It means we are not taking just one plane. If we are taking HKL, suppose we are having 1, 1, 1, then we know that 1, 1, 1 is the simplest form, and that can also be represented, or if we know that this 1, 1, 1 is parallel to 2, 2, 2, 3, 3, 3, 4, 4, 4 to infinity. So, we can say that Miller indices not only specify only one set, but they specify infinite set of equivalent planes. Similarly, the integers are usually written in lowest terms, that is their greatest common divisor should be 1, means we are taking them in lowest terms. And now, by convention, negative integers are written with a bar, as in 3 bar for -3, that we also discussed, because if we are having some intercept on the negative axis, and if we are having some intercept on negative axis, suppose this is -3, then that -3 will be represented as 3 bar. So, here we will have some examples of planes, crystal planes in cubic system. Here we can see this is 1, 0, 0 plane. So, 1, 0, 0 plane, what does that mean? 1, 0, 0 means the dimensions of first one, because we know if we are taking 1, 0, 0, it means lattice constant will be 1, infinity and infinity. It means this plane will be parallel to 1 axis. So, we know that when we are taking a parallel plane, then what will happen when this is parallel, then it will have an intercept. This is parallel to y and z plane, and when it is parallel, then what does that mean? That it will have intercept with y and z at infinity, and it is having intercept equal to 1 at x axis. What is intercept? Intercept is that length which is between intersecting point on the axis with the origin. So, this length is 1 unit or 1 unit dimensions or 1 unit cell dimension along x axis, and since this plane is parallel to y z plane, so it will intersect the y and z plane at infinity. So, we can have the Miller indices for this plane as 1 0 0, because this 1 unit will be 1 by 1 and other infinity will be 1 upon infinity and 1 upon infinity. Now, here what we see, this plane 1 1 0, here we can clearly see that this is parallel to the z axis, and it is having intercept of unit cell dimension along x axis and y axis. So, here the intercept along z axis will be infinity, and so we will have this plane 1 1 0. And now we are taking this plane which is 1 1 1 plane. In 1 1 1 plane, what we see that the intercept along x, y and z is unit cell dimension. So, we will have this plane 1 1 1, and this can be represented here. So, what we see, we see or we saw three different crystal planes for cubic system. Similarly, we can have 0 1 0. 0 1 0 means that plane will be parallel to x and z plane, and that will be having intercept of unit cell dimension along y axis. Similarly, we can define others, and we can ascertain the crystal plane by knowing the Miller indices. So, this is all for today. In next class, we will cover the next topic. Thank you.